All right, everybody, welcome back. This is the second review session for AP Physics 1. We're doing energy and momentum and rotation in this. Now, when you guys took the class, we actually waited a little while before we did rotation. We did that after simple harmonic motion and wave stuff. So I got some feedback from some of you, actually, some of the people in your class, that order didn't make sense to you, and upon reflection, it didn't make sense to me either. So I reordered it for the class this year, and we'll have that other order for the review also. So rotation today instead of what would have been simple harmonic motion for Unit 6 for you. So we'll just kind of start with the basics of energy. Energy is one of those topics that pops up in a lot of different problems, and it could really apply in a lot of different topics as well. So you might have a little conservation of energy thing with rotation or with momentum, something like the pendulum swings down, how fast is it going to move, and then it collides with something. So it's like a conservation of momentum collision problem, but first you have to use energy to figure out how fast it's going to go. It shows up a lot. So it's definitely worth remembering everything we can do with energy in some detail here. And let's see, I'm off the screen a little bit. Let's fix that. There we go. And check camera. Looks good. First thing we do with any of these energy problems is we identify what types of energy are present at different moments in time. Later we'll get to the conservation of energy stuff. The amount of energy will stay the same. Even though the type of energy might change, the amount of energy stays the same. But first we have to be able to identify what types of energy we have in our problems. Kinetic energy, we had that associated with moving things. So anything that's not at rest has kinetic energy. Potential energy, we have a couple different forms for, and this isn't really associated with a single object, but rather with a system of objects. If we have two objects that are separated by some distance, for example, but they're pulling toward each other by this force of gravity, we say there's gravitational potential energy, because they have the potential to fall toward each other. Same deal with a spring, though we would probably usually say the spring is a single object. To understand it, we really have to think about the atoms that make up the spring, and the idea that when we stretch out the spring, we're stretching the bonds between those. So there's this electric force trying to snap it back to its original shape. Or if we compress it, it tries to push it back out to its original shape. So we have both gravitational and spring as types of potential energy. We actually went on a little bit further when we did rotation. We had rotational kinetic energy. So we'll come back to this idea a little later on. And then when we got to electric charges, we talked just very briefly about electric potential energy. The idea that if we have two charges that are next to each other, say they're opposite charges, then they have the potential to snap together, or if they're like charges, they have the potential to shoot apart from each other. So lots of different types of energy. Kinetic is really the only one that's associated with a single object and not with some combination of objects due to their positions and their interactions. We had equations for each type of energy that we dealt with. So for kinetic energy, we did the 1/2 mv squared. So that one's usually the easiest equation to work with of the lot. Gravitational potential. Occasionally we had to use this equation up top here. With this one, we define potential energy to be 0 when our two objects are infinitely far away. Now, when things are really far away, they have a lot of potential to fall toward each other. They can fall through a really big space. So the further away they get, the more energy they have. Which makes it seem a little strange that when they get infinitely far apart, really, really far apart, we would get to 0 for the energy. What we need to do here is pay attention to the fact that there's a negative sign here. 0 is the largest value if all of our other values are negative values. This is really only necessary when we have objects that are moving a really, really big distance relative to each other. So like a meteor coming down to the Earth or something like that. Or when we have two objects that are very similar in size. So the Earth and the Moon, we would use something like this. But if it's a ball falling on the Earth, it's falling a pretty small distance. Even if it's from the top of the building, or a really tall building, it's a tiny distance compared to the size of the Earth. In that case, we use this equation. That's when we have basically a constant gravitational field. So we keep that 9.8 meters per second squared the whole time. So if G is the same the whole time, we'll just use this equation. That's going to be almost every problem that has gravitational potential energy is using this second equation. We get a choice on the second one as to where we define there to be zero potential energy. Usually it'll make sense to have that be at the ground level. If something's resting on the ground, we say it has no potential energy. But we could define it however is convenient for us. It's like if we have the pendulum swinging back and forth, maybe just the lowest position the pendulum gets to is the zero potential energy spot. And then anything above that would have some positive value for potential energy. We're always going to be working with changes in potential energy. So whichever system you use, even though you'll get a different value for the potential energy at a single spot, if you look at how energy changes going from up here to down here, it doesn't matter which equation you use, you get the same change in energy. So that's why we're allowed to have two very different equations to solve for the same thing. Last one that we dealt with in this chapter was spring potential energy. That was 1/2 kx squared. K was the spring constant. So that was how stiff the spring was, measured in newtons per meter. The idea was you apply so many newtons of force to the spring and it stretches or compresses by so many meters of distance. X is going to be how far it's been stretched or compressed from its relaxed length or its resting length, which is not the same as how long that spring is. So if we have a spring that's 1 meter long and then we stretch it so it's 1.5 meters long, X is going to be that 0.5 meter difference between those two. And then that gets squared here. So this equation looks very much like the kinetic energy equation in terms of the 1/2 and the squared term in there. Questions so far? Nobody online yet? I need to check with them. Conservation of energy we can state very simply, but we have all kinds of ways that we can apply this. The idea is just that energy stays the same, the amount of energy stays the same if we're looking at a system where all the forces are internal. So unless we have work being done by something outside of our system, then we don't have any change in energy. So if we think about like an object falling near the surface of the Earth, and the object and the Earth together are going to be our system, we start out with gravitational potential energy because they're separated. We're going to end with kinetic energy for the falling object, and the amounts are going to be the same. The only thing that would change that is if something outside of our system, like a person, walked by and pushed on that ball and pushed it upward, or they caught it as it was falling, then that person is doing work on our system. Work is a change in energy. If they do work, they can either add energy to the system or take energy away from the system. I've been thinking about the work and energy idea lately when I've been over spring break when the weather was so nice. I was pushing Gwen on the swings like every day. She loves the swings. And I was thinking about this how conservation of energy applies. There's air resistance and friction, so she slows down over time. But if we forget about that, I give her a push and she will swing back and forth, going to the same height every time. If I push on her in the same direction as she's moving, so like if I'm standing behind her and she's moving this way and I push her this way, I'm doing positive work on the Gwen swing Earth system. And so they get more energy. And as a result, Gwen goes faster and she gets higher every swing. And if I wait until she's coming back toward me and I give her a little push, like, whoa, she's going too fast, I need to slow her down. She's coming toward me and I give her a push this way, then I'm doing negative work on the Gwen swing Earth system. So they have less energy, which means Gwen slows down and she doesn't get as high. And she gets mad at me and says, faster, faster. Fast, go fast is what she says. So the conservation of energy equation really isn't any different from the work energy theorem, or the two ideas really aren't any different. If we have no work, the work on our system is 0, then our change in energy is 0 as well. We have the same amount of energy for our system before and after some event, or at some initial moment and at some final moment. Now we had an equation to calculate work that we can use sometimes. That was force times distance. I could get that. Oh, I guess I left that one off. Force times distance. If they're not in the same direction, we use a cosine of the angle between those in there as well. Let me get that out. Since I forgot to include it here, it's on your equation sheet, but it's worth seeing the form here. So they combine it all into just one statement here. The change in energy equals the work, which we had just a second ago, which is equal to, this little sign is parallel, that parallel part of this force times the distance. It's like we have a force going this direction, or sorry, a displacement going this direction, but a force upward here. We find the part of the force that goes down in this direction. We break it up into its components. So the part that's parallel to our displacement vector, or if we don't want to go to that trouble in separate steps, we can do it all in one step. So force up like this, displacement down like this, and some angle theta in between those two. Do the magnitude of the force times the magnitude of the displacement times the cosine of the angle between us, between those two. And that's going to be our work, or how much our energy changes by. Okay, so general rules for setting up problems like this. First off, define your system, either in writing or just in your head. Think about what's included in your system and what's not included in your system. So when I'm thinking about pushing Gwen on the swing, I know that gravity from the Earth is pulling Gwen down. There's an interaction between Gwen and the swing. And it's going to be tough to think about that problem if I have that as being an external force, and I have to think about the work done by gravity every time she goes back and forth. So let's include the Earth in that. That also lets me figure out that, well, if we have the Earth and Gwen in the system, then we can have potential energy. A one-object system couldn't have any potential energy. We'd have to just have kinetic energy, and that amount would be changing continually because we continually do work from gravity. So I define my system to be Gwen and the Earth, and the swing, of course, is applying forces to Gwen as well. So include all of those things. And then anytime I change energy from one object to the other, that's okay. I don't have to account for that with the work equation because it's still within my system. The only time I have to do the work stuff is if there's something outside of that system, like me pushing on Gwen, that's going to change the amount of energy in that system. So you don't necessarily have to write out what your system includes and what it doesn't include, but at least think about that. Think about whether our system is losing energy or whether it's just going from one part of our system to another. We need to figure out what two moments in time we want to examine for this problem. So for a pendulum, the two moments we often pick are the moment when it gets to the bottom of the swing and the moment when it gets to the top of the swing. And then we think about what type or types of energy we have at each moment. So for that one, we've got kinetic energy when it's at its bottom, at the bottom point. We have a minimum for potential energy, might as well call it 0. We get up to the highest point, it stops moving for a second there. We have potential energy up there, gravitational potential, and no kinetic because it stops. And then we're going to set the total energy at each moment equal to each other. So the total at the bottom is all kinetic energy. At the top, it's all gravitational potential. So we say starting kinetic energy equals the ending gravitational potential energy. If we've had work done on the system, we need to add that in. So if I gave Gwen a push and I applied 50 newtons of force over a distance of 0.5 meters. That's extra energy that's in our system now. So I need to be sure to add that in. We have more energy on the final side than we do on the initial side. So, and then last thing that we did with these, energy can change forms, or our system can gain energy or lose energy at different rates. And the rate we describe as the power. The verbiage they usually use for this is the power delivered to our system. So if I gave Gwen an extra 30 joules of energy as she's swinging back and forth, and the push that I gave her lasted for half a second, I would say that I delivered 60 watts of energy to Gwen in the swing, at least while I was pushing. Power output you see sometimes too, usually with like motors. You're using a motor to lift something up and giving it gravitational potential energy as it gets higher, and it takes a certain amount of time to get up there. You say the power delivered by, or the power output for the motor. That's it for energy. What questions do you have there?
Energy is joules and power is watts.
Yeah, absolutely. So joules for energy, joules per second for power, or the shorter version of that is watts. If you look at a light bulb, they label watts as a capital W. We already use that for work, so I would probably write out watts. Others? All right. Let's do the next section, which is momentum. Couldn't get the script to work quite right on this, so you might want to add, if you're doing any notes with this, that momentum is a vector quantity. So we should have the little vector arrow up on top of that, and this is velocity, so it should have a vector as well. On your equation sheets, I believe it's written out that way. Yep, the arrows are there on the equation sheets. If you're asked to describe momentum, then make sure you include a direction with it. When we're thinking about total momentum for a group of objects, keep in mind that momentum can be over this way, or it can be up this way, or some angle in between. If we have momentums in opposite directions, they can cancel out. We can end up with no momentum altogether if it's the same amount but opposite directions. So we have to treat them like vectors, basically. Since it's mass times velocity, we measure mass in kilograms and velocity in meters per second, so the units are just kilogram meters per second. For a lot of units, we have abbreviations like kilogram meters per second squared. We just write as newtons. But we don't have one for this one. The direction for that momentum vector is going to be the same as the direction for the velocity vector. So if you know it's moving to the right, its momentum is to the right as well. We have kind of a parallel between energy and momentum. Energy is conserved, and the only time it changes is when we do work on our system. Momentum is conserved as well, and the only time it changes is when we do an impulse. We deliver an impulse to our system. So an impulse, which I don't think J is actually a variable they use on the green sheets. I think your textbook uses an I now that I think of it, so I'm not sure why it's a J, why I have a J on there. Yeah, that's just wrong. That should be an I. Impulse we define as the force acting on something times the duration of the force, how long the force lasts. It's an important quantity because we can rearrange Newton's second law to give us this equation. So Newton's second law is acceleration equals force over mass. And acceleration is the same as delta V over delta T, change in velocity over change in time. So we can rearrange that to get to this statement and find that our momentum will change if we have a force applied over some time. It changes by the product of that force and that time. So the impulse momentum theorem just says the impulse given to some object is equal to its change in momentum. And so again, this is a J, but it should be an I here. I equals delta P. Page.
So the units could be kilogram meters per second. Is that also a unit for momentum? What were the units for momentum?
Yep, momentum is kilogram meters per second also.
Okay.
And technically you could use Newton seconds for momentum as well. They're equivalent units. Newtons, remember, are kilogram meters per second squared. So then if we multiply that here by some time in seconds, we get one factor of seconds canceling. We just get to kilogram meters per second. If we're saying that the impulse equals the change in momentum, they're equal to each other, it makes sense they would have the same units as well.
Mm-hmm.
So just by convention, we usually use Newton seconds for impulse and kilogram meters per second for momentum, but they mean the same thing, so they're interchangeable.
Okay.
One thing we talked about with this equation was the idea of like safety equipment. If, say, you're moving at some speed and you're going to come to a stop, you have some mass and some change in velocity that's well defined. There are really two ways to get that done. You can apply a big force over a small period of time or a small force over a big period of time. If it's a person who's doing this, this motion, we certainly would prefer a small force over a big period of time. Big forces do damage. So we have things like airbags that slow us down more gradually than hitting the steering column does. Or brakes to slow down our car more gradually than running into something would. So safety devices, that's a big application for that, that equation. If we don't have a constant force, that impulse can seem a little tougher to calculate. We have force times time, but do we use the starting force or the ending force or the average force? It turns out actually average force would work. Sometimes though, they'll set it up with a graph. And so on this graph, if I just had a horizontal line here, and you found the area underneath that horizontal line, it's a rectangle then, our area would be, say this is a horizontal line, our area would be, well, the 20 newtons is our height, and then whatever, 8 seconds is our width. Multiply those two together, and we get 160 Newton seconds. And from the units, you can say, oh yeah, Newton seconds. So that's a force times the time. That's impulse, yeah. Well, it works even if it's not a constant force too. So here we have a change in force where it's increasing for a little bit, and then we have a constant force, and then it's decreasing. If we found the area inside this trapezoid, that's going to be equal to our impulse, which we know is equal to our change in momentum. If they give you a complex curve, where you can count the squares, how many squares roughly are underneath that curve, and then figure out how much each square is worth. What's the area of each square? And that gives us our total impulse. Something like this, just use the area equations. If you don't remember for a trapezoid, the area equation, just break it up into a triangle by drawing a line here, and then a rectangle and a triangle by drawing a line there. We know that momentum is conserved unless we have an impulse delivered. So what we typically write for this is that the total initial momentum equals the total final momentum. The image here is just the Newton's cradle desk toy thing, which is a nice illustration of that, that we have this collision where we have some ball hitting the other ones at some speed, and then we're going to have one ball leaving at that same speed. It's the same mass, it has to have the same speed in order to have the same momentum. Momentum is conserved there. If we have two balls that we drop at the same time, we can have two balls leave. We have to have the same momentum, leave at the same speed due to energy considerations that we talked about briefly. So in order to have the same momentum, we have to have the mass of two balls again. We start with this equation in solving these, and then the very next line is going to be something like mass of object A times initial velocity of object A plus mass of object B times initial velocity for object B. equals mass of object A times final velocity for object A plus mass of object B times final velocity for object B. If we have more than two objects, we'd have a C term or a D term in there. If we have two dimensions in there, which is possible, though I don't think they do that really on the AP test. If we have a two-dimensional problem, we could break it up into X and Y velocities. So mass of object A times the initial X velocity of object A plus mass of object B, and so on like that. And then the same thing for Y's. But I think you'll just be working with one-dimensional problems like that. But start with that equation so they understand that you get where all this stuff is coming from. Oh yeah, momentum is conserved, to show them that you understand that just by writing this equation. And then work from there. With momentum, we dealt with a lot of different collisions. And we talked about different types that varied in terms of how much energy we have transferred from kinetic to other types. If we have an elastic collision, that means is that whatever energy we start with as kinetic energy ends as kinetic energy also. So for an elastic collision, not only could we say MA, VA initial plus MA, or MB, VB initial, yada, yada, yada. You could also do the same thing with kinetic energies. 1/2 times mass A times initial velocity A squared plus 1/2 times mass B times velocity B initial squared. And the same thing on the final side. Elastic just means that all of our kinetic energy, it doesn't really stay kinetic energy. So we get these things colliding and we get some stretching and compressing as a result of that. But then when they spring back, all that energy gets back to kinetic energy. We call that the restoration, not the conservation, but the restoration of kinetic energy. Basically, it means that you get to solve a system of equations instead of just a single equation. Yay! Inelastic collisions, all that tells us is that we have some of our kinetic energy that doesn't get restored as kinetic energy. So some of it goes to making the objects warmer. You have two things and they collide, and it makes the atoms in those two things jiggle more than they were a minute ago. So we haven't lost any energy, it's just not kinetic energy anymore. It's harder to observe energy. And then the last one, completely inelastic or totally inelastic or perfectly inelastic. That means that a maximum amount of kinetic energy has been lost or changed into other forms. The consequence of this, the thing that we can observe and work with for our equations, is that the two things stick together in a completely inelastic collision. So when we do the momentum conservation stuff, we'll have a term for object A and a term for object B to start with, but then on the other side we'll have just mass A plus mass B combined. Just one object moving at one speed, one bigger object moving at a single speed. So these ones are nice because you end up with fewer terms. They're a little simpler to solve. All right, that was it for the overview on momentum. Questions there? Okay. And then last one is rotation. These are just screenshots from the notes that are posted for rotation on the website. So if you don't get all this, or if it's tough to read, you can see those there. The presentations also I emailed to you, so you can see them that way. With rotation, one thing we talked about here is that we have rotational kinematics variables and equations that we can use. For position in linear stuff, we used an X or a Y, but for rotation, we use a theta. So if we have like some circular disk and it rotates halfway around, we could say it starts at a position of 0 and ends at a position of halfway around a circle would be pi radians. Position in terms of meters is a little tricky with something like that because if it's staying here the whole time, it's not really moving from place to place. We could watch maybe one spot on the edge of it and how far that's moving. But it's kind of a tricky way to express it then. So we find that the rotational or the angular quantities, we call these angular quantities, sometimes those are easier to work with for certain problems, especially for rotation problems. So instead of velocity being v or v naught, we use omega or omega naught. And it's not going to be meters per second, it's going to be radians per second. Instead of acceleration being a, it's going to be alpha. That's a little tough to read probably, but that's the Greek letter alpha. It's like the fish symbol. And it's not going to be in meters per second squared. It's going to be in radians per second squared. Time doesn't change. Still measured in seconds, still using a lowercase t for that. And then we have these three kinematics equations that we've dealt with for the linear motion. We can use those same three with rotational motion. They're exactly the same equations, just every time we have an x, we're replacing it with a theta, every v gets replaced with an omega, and every a gets replaced with an alpha. And these equations are on the equation sheet as well. As are the meanings for these variables. So like it has down at the bottom, omega equals angular speed or rotational speed. So sometimes you'll actually have to do kinematics equations with the rotation stuff, probably in connection with a torque of some sort. We have an analogy between linear stuff and rotation stuff in terms of the position and velocity and acceleration and how we describe those, and also what would cause an acceleration. With linear stuff, acceleration is caused by having some unbalanced force. With rotation, rotational acceleration or angular acceleration is caused by having an unbalanced torque. If we think of this situation where we have, I think I described this as like a door from above, where this is the hinge for the door and then the handle would be out here. If we're applying some force that's shown there to the door, and it's some distance r away from this center of rotation, and we can calculate the torque as that distance times the magnitude of the force times the angle between those two. So this force points up and to the right. The part that's to the right, that doesn't make this door rotate. It's only the part that's upward that makes it rotate. This is just straining it against the hinges. So really we're doing F sine theta, which would get us this component of that force, the up and down component of that force, times the distance away from that center of rotation. That gets us our torque, and we use the Greek letter tau for torque. And then we have analogs for Newton's first law and second law with rotation as well. So with linear motion, we said an object is in equilibrium. That means it's not accelerating. So the net force on it has to be 0. If it's in rotational equilibrium, that just means its rotational motion isn't changing. It doesn't have any rotational acceleration. So the net torque has to be 0. We can have forces that are causing a torque, but the torques have to balance each other out. I didn't include it here, but back to this, the units for torque are important here. We have a distance, which will be in meters, and a force, which is going to be in newtons. We use Newton meters for the units of torque. If you think back to the work stuff, that was work as in joules, but we calculate it by doing a force times a distance, so newtons times meters, that's equivalent to joules. Here, Newton meters is equivalent to joules, but we're not going to ever use joules for that. Again, just by convention, even though they're equivalent units, We never use joules when we're talking about torque. It gets too confusing, I guess. Are we talking energy or are we talking torque here? So we keep it as Newton meters. So we might be in rotational equilibrium if we have no forces trying to twist this object, or maybe we have one force that causes positive 25 Newton meters of torque and another one that causes negative 25, or 25 clockwise and 25 counterclockwise. So they balance out and our thing either doesn't rotate, or if it's rotating, it keeps rotating the same speed. If those torques don't balance, we have Newton's second law to account for that. The net torque is equal to I, which we call the rotational inertia, sometimes called the moment of inertia, times alpha, the angular acceleration. So this is probably where the kinematic stuff will come in. We're applying these torques and it's rotating at this angular speed. What's the angular speed going to be after 5 seconds? Well, we'll calculate angular acceleration and then go to the kinematic stuff. So net torque, we just add up the force times distance times cosine of the angle for every force on this, about some axis of rotation. Rotational inertia is how much an object resists changes to its rotation. Mass and inertia go together. That's how much an object resists changes to its linear motion. This is how much it resists changes to its rotational motion. So this depends on the mass of the object and how that mass is spread out. So you might have remembered from class we had like a meter stick with 2 heavy weights on the end, and then another meter stick that had those 2 weights in the middle. And if you try and shake the one with the 2 weights in the middle, it's pretty easy. With the 2 weights on the end, it's much harder and you have to go much slower going back and forth. There's more rotational inertia on the one with the weights at the 2 ends. To figure that out for point masses, like the 2 weights on the ends or the 2 weights in the middle, the rotational inertia about whatever axis we're going to rotate it around. So if we're trying to rotate it around the middle of the meter stick, we'll measure everything from the middle of the meter stick. We just do the mass of something that's attached to the meter stick times its distance from the middle squared. So I think we had 1 kilogram masses on that meter stick. If we ignore the mass of the meter stick, we'd have 1 kilogram times 0.5 meters squared. And then there's another one on the other side, so another 1 kilogram times 0.5 meters squared. And so that's going to give us 0.25 kilogram meters squared for each one. Add them together and we get 0.5 kilogram meters squared for our total. When they're right near the center, that R distance isn't going to be the full ½ meter, it's more like 2 or 3 centimeters away from the middle. So we get a smaller rotational inertia. It just means it's easier to rotate. Questions so far? Our textbook and the review book that you have both have tables of some common shapes and how we would figure out their rotational inertia. So what they've done here is they've thought about each atom on this thing is a certain distance away from this axis of rotation. So for each atom, let's do the mass of the atom times the distance away from the center. And since there's lots and lots of atoms, they do it more as atoms per space or mass per area or per volume. And they integrate that. So it's calculus stuff that gets us to these equations. We don't have any calculus requirement for this class. So if they want you to figure out, say, the rotational inertia for a solid sphere, they would just give you this equation, either in a table like this, or they would just say, hey, here's the equation for the rotational inertia for a solid sphere. All right. Just like with the stuff we've been doing so far, we have a rotational analogy for energy, or analogy for analog. In this one, it's going to be, hey, welcome.
Hi, Mr. Bennett.
In this one, it's going to be rotational kinetic energy is equal to, looks very similar to what we had for regular kinetic energy. That was 1/2 mv squared. Here the I, rotational inertia, takes the place of m, which is like the linear inertia. And omega takes the place of v. Omega is the angular speed, takes the place of linear speed. So if we have some object that's spinning, it has energy, it's energy of motion, even though it's not moving from place to place. So I have to do work to get something spinning. Got that big, it's right here actually. Got this big bicycle wheel, right? And I have to push on it, apply a force over some distance to get it moving. That energy doesn't just go away. We can see this thing is moving from place to, well, the object as a whole is moving from place to place, but each part of the wheel is going around. It has some speed. There's kinetic energy present. So we keep track of that energy with the rotational energy equation. Where this gets tricky is when we do the conservation of energy stuff. Sometimes, like if we have something rolling down a hill, that thing will be gaining both linear kinetic energy and rotational kinetic energy, or translational and rotational are words we use for those as well, as it loses potential energy. So you have a 3-term equation there. Potential energy is decreasing, translational and rotational kinetic energy are increasing, so we have to work with all those simultaneously. So that can be a little tricky. And last thing, I believe, is rotational momentum. Again, another analog from linear stuff. We still have conservation of momentum. Now we're dealing with rotational or angular momentum. Instead of it being mass times linear velocity, it's the rotational mass or rotational inertia times the angular velocity to get angular momentum. And same deal as before. If we don't have any forces from outside, any torques from outside of our system, then our angular momentum is going to be conserved. And so we can say the total initial angular momentum equals the total final angular momentum. If we do have forces and torques from outside of our system, then we're going to have a change in our angular momentum equal to the total torque times the amount of time that it's being applied. So with momentum, linear momentum, we had delta P, the change in linear momentum, equals force times delta T. So here, linear momentum is replaced with angular momentum. The force is replaced with torque. So it follows in step with how it's set up with linear stuff. The big example that we use for angular momentum is if we have something that's rotating and maybe we drop something on top of it, or we change the shape of that thing, or maybe it's leaking. We get a bucket of water rotating and it's leaking water or something. Some characteristic of the mass or how that mass is distributed changes. How does that affect the speed? We'll say, there it is. Even though our mass or our moment of inertia, rotational inertia, or rotational momentum or velocity, even though one of those quantities has changed, the momentum has to stay the same. So something else has to compensate for that. And that's it for rotational momentum, or rotational stuff in general. Questions there? Okay. Well, we're at about the 1 hour mark, which is better than I did last time. Let's do some problems with this. There we go. Okay. I just pulled these from the review, or the practice tests that have been published. The one that's been published, I guess. So some of these questions probably look familiar, but that's okay. They ought to look familiar. This is a review. So we'll think through how to set these ones up again, and I'll kind of talk you through my work on these also. So first one is dealing with the angular momentum, angular motion stuff again. Sorry if it's a little tough to read. Manu online, you can check. I sent an email out, I think last night, with links to these presentations. You can check that if that's easier for you.
Okay.
But yeah, why don't you take a few minutes and see what you can do with this one, and we'll talk through it. Ready to go on this, or you want a little more time? Okay, so what are we thinking for this one?
Well, I said A, but it could also be B, if that one's right.
Okay, child moves toward the center, increasing the total angular momentum, or the child moves toward the center, decreasing the rotational inertia. So one of those two?
Probably A, because you decrease the rotational inertia. How's that? That would
Okay.
help it go faster. You look at inertia is like it wants to keep moving.
Uh-huh. Okay, gotcha. Other thoughts? Okay. On this one, if we have our child moving toward the center of the platform, our child and the platform are moving together. They should be treated as a system. So any forces between the child and the platform, like the friction between the kid's feet and the platform, that's an internal force. If there were a torque, it'd be an internal torque as well, which means it's not coming from outside our system. If there's no external torques, we can't change the angular momentum. That's got to stay the same. So A can't work because the kid, while they're riding on the merry-go-round, can't provide an external force. We'd have to have maybe somebody standing on the side and giving it a push to provide that external torque, external force. For part B, the child moves toward the center of the platform, decreasing the rotational inertia of the system. Well, if they move toward the center, that would definitely decrease the rotational inertia, since that's a measure of the spread of the mass. If the mass is less spread out, then yeah, rotational inertia goes down. The question is, will that make the angular speed go up? Yeah, actually it will, because angular momentum has to stay the same. So angular momentum is the rotational inertia times, I'm sorry, you weren't asking a question, were you?
No, I wasn't.
Oh.
I don't understand the difference between momentum and inertia.
Okay, so inertia is a resistance to changes in momentum.
Okay.
So if we have some value of momentum, it's really easy to change if we have a small inertia, and it's tough to change if we have a bigger inertia.
Okay.
All right, cool. Since we don't have any external forces or external torques on this, we know momentum is going to stay the same. Momentum here is the product of angular speed and the rotational inertia. So if rotational inertia goes down, angular speed has to go up. This is exactly the same problem as the ice skaters spinning around with their arms out like this, and then they bring their arms in and they start spinning really fast. The same thing. We bring our mass in closer, and we increase our speed at which we're spinning. Way more fun with hand weights on a desk chair, by the way. Bring those in. Make yourself sick doing that. Lots of fun, right? To make yourself sick.
So if you decrease the inertia, then it makes it so it can speed up. It's not as hard to change the momentum.
We're not trying to change the momentum in this one. We're changing the speed so that momentum doesn't change.
Okay.
Now, if we look at C and D, they're backward here. If the child moves, if they move away from the center of the platform, we increase the total angular momentum of the system. Again, momentum doesn't change. So C and A are wrong for the same reason. And then D, the child moves away from the center, decreasing the rotational inertia of the system. Well, that's just wrong because it wouldn't decrease the rotational inertia. It would increase the rotational inertia. So D is wrong because it's got the definition of rotational inertia wrong. So this one doesn't have to be B. Questions there? Okay. Number 4, this is a favorite already. It's only been out for a year, and I've heard all kinds of complaints about this one.
Was there a question on this one?
Maybe. We've solved it at least once, or we've answered this at least once before, yeah. I don't know if it was on the final or just practicing class. But yeah, we've done this one. This is a new problem type for this year in AP Physics. They're not asking you to make a calculation. Instead, they're giving you information and asking, can you make this calculation? Do you have enough information to solve this one? They used to test your abilities with this by giving you extra information and seeing if that would throw you off. Here, they're giving you enough information to find some things, but not find other things. And you have to state whether you can find these things or not. So on a problem like this, I would go through each choice and think through, what would I need in order to solve this? We have 2 things that we're looking at here: angular speed, or the change in linear momentum, or both, or none of these. So based on this information, can I find angular speed? If yes, then I can eliminate B and D. If I then go on and can find the other quantity, I know it must be C, otherwise it's A. So let's think about how we would calculate each one of these things. Angular speed. Angular speed, that's a measure of how rapidly it's spinning. How many rotations it makes per second, or how many radians it goes through each second. So I would need to have some way to tell how long it takes to go a certain distance around. Now, it doesn't state that directly here, but we can kind of get an idea from the graph. I know on the screen it's probably a little tough to tell here, but these are actually a little different colors. This one's kind of a gray, and this one's a black. corresponding to the two different balls on here. So if we have it spinning in this vertical plane, the overall moving downward, but sometimes they're, because of their rotation, they're moving a little faster downward if they're rotating in that direction, or sometimes they're moving a little slower downward if they're rotating up. If we looked at how that speed changes along this line here, looked at how that speed changes, the high points must be when that ball is moving downward. The whole thing is moving downward. If we get higher than the average there, that must be it's moving downward in its rotation as well as the whole thing falling down. So if I like to, like this point, that's where, like I said, it's gray on the picture. That's where the gray object is moving downward. And then here it's below the average line there, so it must be moving upward here. And then up here it's at another maximum, must be moving downward there. So I've identified 2 points where it's moving downward. It moves downward in this case when it gets all the way over to the right side. That's when it's moving down the most. And so those 2 points on the graph are going to be where it's at that position on the far right side. In between those 2 points, it made one complete revolution. And in between those 2 points, it took, well, this is at about 0.8 seconds. Got about 0.8 seconds here, and then moving upward, and then moving downward here. About 2.8 seconds there. So that's one complete revolution in about 2 seconds. Doesn't matter if my numbers are wrong here. All I need to do is say, yeah, I've got information about how far it's gone around the circle and how much time it takes. We can calculate angular speed. In this case, it's going to end up being about 2 pi radians divided by 0.2 seconds. Yeah, 0.2. Doesn't matter what the number is, just the fact that we can do it is enough. So yes, we can find angular speed, which means we eliminate B and D. So the question is whether it's A or C. Can we also find linear momentum? Well, or the change in linear momentum from 0 to 0.3 seconds. If I want to find linear momentum, I need to know the masses of these objects and how fast they're moving and how that changes from 0 to 0.3 seconds. So take a look at the graph and the information that's given to me. Do I know the masses of the objects first off? Masses are given, yeah. 0.6 kilograms. Do I know starting speeds for each of these objects? Looks like it's 0 for both of these right here. And do I know the speed at 0.3 seconds for each of these objects? Here and here. So I can find the momentum of one of the balls at the very beginning, and the momentum of the other ball at the very beginning, and the momentum of each ball after 0.3 seconds. And I can subtract those two values from each other. So add up the total momentum, 0.3 seconds, subtract that or subtract 0 from that, since they both start with a 0 velocity. Yeah, it doesn't matter what the numbers are. We're just looking for the fact that, yes, we can solve for that change in linear momentum. So C is the way to go on this one. We can find both of those things. Questions on that one? The answers to these and some explanation for each of these are included in that file I shared with you, or the folder I shared with you yesterday also. More rotation on this one. I noticed, by the way, looking at those practice tests, there's a lot of rotation in those tests. So this would definitely be a unit I would spend some time reviewing. And it's a tricky unit, so spend extra time for that reason reviewing this stuff. Do extra practice problems on rotation. Ready to go on this, or should we take another minute? No feedback? Perfect. All right, let's go through this. Thoughts you want to share first? Ideas you had on how to approach this? This thing does not take long to turn on. Okay. Assuming that everybody understands perfectly and they just don't want to show off. I'll just explain for the people who aren't watching live, because some of them might be confused about this. All right. Our answers on this give us a clue about how to think about this problem. We think in terms of energy. All right. They have the same mass, and they start up at the top of the same kind of ramp. They're both stationary to begin with, so they both have nothing but gravitational potential energy to start, and it's going to be the same amount, because mass and height and gravity are the same amount for both of them. So same total amount of energy in either case. It says the ball rolls without slipping. So it's going to be moving down the ramp, but as it does, it's going to be rolling. The block slides down the ramp, but it has no friction on it, so we don't have to worry about work done by friction or energy changed into heat or internal energy. So it's all staying in easily observable forms. The block is just going to be getting translational kinetic energy. It's moving from place to place as kinetic energy as a result. It's losing potential energy, it's gaining kinetic energy. So as it goes down the hill, it gets faster and faster as a result of having more translational kinetic energy. When it gets to the bottom, all of that potential energy it started with has been changed into translational kinetic energy. The sphere, on the other hand, is not only moving from place to place, it's also spinning, or it's rotating. So it has both translational and rotational kinetic energy. We don't have to worry too much about how much of each it has. Just the fact that some of that energy that it starts with is rotational kinetic energy now tells us that when it gets to the bottom, that ball has less translational kinetic energy than the block does. Translational kinetic energy is 1/2 mv squared. Since they're both the same mass, we can also say then that the block must be moving faster from place to place than the sphere is. That's true at the bottom of the ramp. It's true at every other point along the ramp after they're released. Some of that energy for the sphere doesn't go toward moving it from place to place. Some of it goes toward spinning that sphere. So the block is always moving faster after they're released than the sphere is, which means the block must get down to the bottom faster. Now this question is a little tricky too, because it doesn't just ask which one gets down to the bottom. That's the old style of question. Which one gets down there first? And the answers are the block or the sphere, or they both get down at the same time, or there's not enough information to tell. That's the old style question. This one requires you to pick the right answer and the right justification for it. So we know the block gets down to the bottom. Which reaches the bottom of the ramp first? The block. So that narrows it down to C and D. Now we have to pick the justification. The block, because it does not lose mechanical energy due to friction, but the sphere does. Or the block, because it does not gain rotational kinetic energy, but the sphere does. Well, we assumed that they both kept all their energy here. The sphere would only be losing mechanical energy due to friction if it were sliding, if it were being dragged across the ramp there. We had kinetic friction there. We do have friction, but it changes some of that energy into rotational energy rather than changing some of it into heat. So in this case, D is the way to go. The idea that the sphere is getting some of its energy changed into rotational kinetic energy, so it's not all translational, which means it's not all related to how fast it's going from place to place, which means it's not going as fast as the cube, which means it doesn't get to the bottom as quickly. Tricky question type, for sure. Having the justification part in there, that really adds a level of depth of knowledge required to solve this. Questions about that one? Okay. Hey, a non-rotation problem. That's fun. Take a look at this one. All right, everybody. What are your thoughts on this? What's important for us to pay attention to in this problem in order to get to an answer?
Power is equal to change in energy.
Okay, so we need to know something about energy for each one of these, if it's energy over time.
Energy's like work.
Mm-hmm.
And they have the same force and the same distance.
Is it the same distance? Do we have that information?
No. It's the same time.
Okay, same time, we know.
So, distance of what? I don't even know what I'm looking for.
Okay, so the idea with force times distance is we take one of these boxes and we push it, and then eventually we stop pushing on it. How far have we traveled before we stop pushing on it? So let's think about that. If we have two blocks that are different sizes, different masses, and we push on both of them for the same amount of time, do they go the same distance? Same force, same time, but different mass, do they go the same distance?
No.
Which one would you expect to go farther? Yeah, the little one, you bet. So the idea here is that with the same force, the little mass accelerates more than the big mass does, which means it travels farther. So if you looked at that force times distance to figure out work, the little one has a bigger distance, so more work is done on it. It takes the same amount of time. It takes from 1 second to 2 seconds for each of these. The little one goes farther, so it has more work done on it. Work divided by time gets us power. So the one with the greatest power delivered to it then must be the little one. What they're doing here is they're trying to set you up to just find the area under this curve, thinking, ah, yeah, area under a force curve, that's equal to work. Man, same for both of them because it's the same curve, so same work, same time, same power. Bam. It's not that way, though, because this isn't a force versus distance graph, or force versus position. That's the kind of graph where the area under the curve equals the work. On this graph, the area under the curve equals the impulse, or the change in momentum. Force times time, not force times distance. Sneaky of them, very, very sneaky. Questions on that before we move on? All right. Sorry, another rotation one. I had this idea the other day, having an active select your answer with your red dot as we get to it. Pretty slick, huh? And, you know, shine into people's eyes while we're waiting. Oh, wait, don't. That's what I mean. Question mark.
A through B. Okay,
All right, well, let's go ahead and get some answers.
I'm guessing it's me.
Andy. All right.
it just doesn't sound right.
Just doesn't sound right.
It's kind of how.
Okay. This is another one of those tricky ones where it's not asking for the answer, it's just asking for how you would approach the problem. You would think that just getting the answer would be trickier because you have to know how to approach the problem to get the answer. But I think these ones are harder than the old style where it just said, you know, find a number based on these other numbers. All right, well, let's look through these. Determining the distance of the moon from the planet at point B in terms of the given quantity. So in terms of the other distance and the two speeds. We're going to use, let's see, A is conservation of angular momentum. So it's either conservation of angular momentum or conservation of energy for these ones. Okay, so we'll keep that in mind. That's one choice we have to make. And then the other one we have to make here is our rationale, because gravitational force is the same on the planet as it is on the moon, or because gravitational force is directed toward the planet. Okay. We're looking at the motion of the moon around the planet. We're treating the planet like it's stationary in this problem. Even if it's not stationary, we don't care about the motion of the planet. So if we start with a rationale about the force acting on the planet, that's probably not going to be useful for us because we don't care about forces on the planet. We just care about forces on the moon. So that, to me, narrows it down to not A and not D, because that one's talking about how big the forces on the planet are. I don't care. Yeah, they're the same size. Newton's third law. Yeah. Doesn't matter for this problem, though. So that narrows it down to B or C. We have a gravitational force on the moon that's directed toward the planet. Does that tell me that I can use conservation of energy, or does it tell me that I can use conservation of angular momentum? Angular momentum is conserved when we have no torque. If we have torque applied over some time, then our angular momentum changes. So, the question now is, does that statement that gravity is directed from the moon toward the planet, is that telling us that there's no torque? Yes, it is telling us that. So if we have, let's show this all here. If we have There we go. If we have a force directed right toward the moon, or right toward the planet here, force is directed toward the planet. To get torque, we do the distance from the center of rotation to where that force is being applied. So that'd be from the planet to where that moon is, so point A or at point B, I guess. I don't know why I drew the arrow up top there. It should be at point A or point B. We'll fix it. There. Or there. Okay, so those are our forces in blue. And then our position vectors, I'll draw those in red. Apparently not. Okay, position vectors in red. That's from the center of rotation, which is at the planet, to the location of those of the moon in each case. And then torque is equal to R d cosine theta. And the theta there is the angle between, or sorry, sine theta, not cosine theta. The angle that we're talking about is the angle between the displacement vector, the r vector here, and the force vector. Those are in opposite directions. So the displacement vector points from the planet to the moon. The force vector points from the moon back to the planet. They're opposite directions, so our angle there is 180 degrees. What that means basically is that we don't have any torque because our force isn't down this direction, speeding it up along its rotation, or up this direction, slowing it down, or up this direction, speeding it up, or down this direction, slowing it down. It's directly toward the center of that rotation, not along the outside. So it's not going to speed us up and it's not going to slow us down. There's no torque caused by that force. So we have to have, then if there's no torque, a constant angular momentum. The fact that there's no torque doesn't tell us anything about energy. Questions on that one? Now, in this problem, you actually could solve this using conservation of energy. So if you know the distances and you know the speeds, we have this change between gravitational potential energy and kinetic energy. But the fact that we have an equal, so here, the fact that we have an equal force on each object, or the fact that that force points toward the planet, that doesn't have anything to do with conservation of energy. So we could use conservation of energy. It just doesn't match with either of the justifications they give us. That is a really tough question. And I nailed it. Go me. Woo! Make you feel better? All right, let's move away from rotation then. That makes everybody feel better. Okay, are we ready to share answers? Oh, okay. Wait a minute. Good to go? All right, grab the laser pointers. What do we come up with? Okay. Cool. Block 2, because the final velocity is closer to the initial velocity of block 2 than it is to the initial velocity of block 1. Absolutely. That's absolutely right. D is the correct answer on this one. Greater mass, so that means that it has a bigger resistance to change. So when they come to stick together, the one with the bigger mass will change less, the one with the smaller mass changes more. So D is consistent with that. A and C are silly answers on this one. Block A, or block 1 has the greater mass because it has the greater speed. Ah, yes, because things that are bigger have to move faster than things that are smaller. No. B, is legitimately something that somebody might pick here, but between B and D, it's got to be D. Yeah, it's just the wrong answer. Yeah, it's at least a sensible answer, just wrong. Sensible.
Like if the velocity of blocks 1 and 2 was a little greater and was closer to block 1, would that answer make sense?
Yeah. So if let's see, block 1, that would have to mean that maybe our velocity ends up here instead of down here. Then B would be correct. Same graph on this one, but a different question. I think this is the graph for questions 10 through 12. Ready to go? Okay. Let's go ahead and share your answers. And Manu, I kind of been leaving you out. If you just want to say your answer, you're welcome to. If you'd rather not share, that's fine too.
Sure, I think it's A.
I think it's A, okay.
Maybe.
Is that you?
Got some trouble with the lasers up here. All right, looks like A or B in class here. Okay. Well, let's look at B first. And this idea right here. Some of their kinetic energy cancels. If we had some of the kinetic energy canceling, what that would have to mean is that we have some positive kinetic energy from one and some negative kinetic energy from the other. Is that possible?
No.
It's not possible, yeah. We can't have negative kinetic energy. Look at the equation. It's 1/2 mv squared. Even if v was negative, when you square it, we get a positive number. kinetic energy is a scalar quantity, and it's always a positive quantity. So to have some of it cancel just can't happen. So it doesn't matter what the rest of this one says. The fact that it's saying some of their kinetic energy cancels tells us, yep, that's wrong. Throw it out. Leaves us with A for the choices we made here. It's less because the blocks have the same velocity after the collision. So some of their kinetic energy was transformed into internal energy. Yeah, that's absolutely the case. This one, by the way, you could answer just by knowing what we call this type of collision. When they move together after they collide, what type of collision is that?
Inelastic.
A completely inelastic collision, yeah. Inelastic collisions in general, we have some of our kinetic energy transformed into internal energy here. It goes to making the thing shake. Now, in the case where we have none of our kinetic energy transformed, we have this process where our things kind of come together and they smush together for a second, but then they boing, spring back to their original shapes. Here, we don't have that boing, right? We stop when they're smushed together. So their shapes have changed a little bit, and all the little particles in there are shaking a little more than they were. You're jiggling. Richard Feynman would say they're jiggling more. Questions on 11? Fantastico. Let's go on. One more for the same graph. All right, looks like you're ready. Go ahead and pick some answers here. It's very hesitant lasers there. I'll move generally in the direction of the questions and see where the other dots show up. Okay, looks like B or C. Maybe A. I can't tell where that last one went. That one was going crazy. Manu, do you want to share yours? Oh, I'm getting attacked by him now.
I think it's
I'm sorry, which one?
B.
B, you think? Okay.
Yeah.
All right. Well, let's think about, first off, center of mass. Center of mass is just, if we have all these objects in our system, they each have their own mass, let's add all those masses together and treat the system like it's one single mass, and the location is right in the middle of all that big mass of masses. Now here, we have something we can say about the center of mass at the end. For sure, these two masses are moving together at the end. So however they're moving, that's how their center is moving as well. At the end, for sure, we've got a center of mass movement of plus 1.0 meters per second. So we can get rid of anything that doesn't have that as a possible answer here. So let's see, center of mass does not move. Well, we know afterward it moves at 1.0 meters per second. So definitely that one's wrong. Center of mass moves at a constant 1.0 meters per second because there's no friction acting on them. Well, we have to decide if it's constant or not. We'll come back to that. C, the center of mass velocity starts out greater than 1 meter per second, but decreases to exactly 1 meter per second during the collision because the collision is inelastic. So that still has the 1 meter per second in there. That is possible still, B or C now. Or D, the center of mass velocity increases as the blocks get closer together and then becomes constant after the collision. Well, that one's still possible too if all we know is that they have a constant 1 meter per second speed after they collide. The center of mass, or the system as a whole, will accelerate, will change speeds only if there are external forces on it. The acceleration of the system is equal to the sum of the external forces divided by the mass of the system. Are there external forces acting on this system, acting on these two blocks? Not that we know of. If there were, we would expect that here we'd have some non-constant speed, and here it'd be non-constant, and here it'd be non-constant. It looks like we have constant speeds before the collision and constant speeds after the collision. So it must be that we don't have any external forces on this. If external force is 0, then acceleration for the system is 0 as well, which means our center of mass moves at a constant speed. We knew that it was going to be 1.0 meters per second after the collision. If it's constant, it must be a constant 1.0 meters per second. So B is the correct answer on this one. Questions on number 12? All right. 22, and I think this is the last multiple choice one, and we'll just get started with the free response question before the end. If we don't finish it, then just check on the files that I shared with you. It's all available there. Notice on this one that it is one of the multi-correct questions that would be at the end of the multiple choice section. So this one you have to pick 2 correct answers, and they have to be, both of them have to be correct to get the points. All right, everybody pick 1 correct answer right now. Oh, looks like we got a flickery one there. Okay, A and B are the ones that are selected right now. If you had an idea for what the second correct one is, why don't you go ahead and select the other correct one then. Okay, so we have A, B, and C right now shown as our possibles for 2 correct answers. So looks like a pretty good spread on the answers in class here. So we'll go through this one for sure. Kinetic energy. Well, one thing I know pretty straightforward on kinetic energy is that it's equal to 1/2 mv squared. So if I were to graph this versus the speed, the equation for the graph would be basically y equals 1/2 times the mass times x squared, where x is the speed. So I'd expect a graph that looks like an x squared graph, y equals x squared. That's a parabola, not a straight line. So I know that the speed can't possibly be the thing that's on the x-axis. The equation is a quadratic equation, not a linear one. So I can eliminate C. I think on these multi-correct ones, That might be a better way to approach this than trying to find the two correct answers, is try and find the two incorrect answers. That might be easier on some of these. So we eliminate C. Then it's a question of whether it's time elapsed, distance traveled, or magnitude of the net work that's incorrect. Well, let's start at the bottom, work our way up. We've already eliminated C. D, magnitude of the net work done on the block. Well, work is equal to force times distance, or another equation we had for work was change in energy. Ooh, kinetic energy, that's energy. As we do more and more work on this, that work that we're doing, it turns out is negative work because our kinetic energy is decreasing. But we're just looking at the magnitude of the net work. So as we do more and more work, our kinetic energy is going to go down the same amount. If I do 50 joules of work, my kinetic energy decreases by 50 joules. That's a linear relationship. In fact, it's a 1-to-1 ratio here. So D actually does fit. We could have the magnitude of the work for our x-axis. So that's one of our correct answers. All right, now part B, or answer B, or answer A. That's what we have left. We're just working our way up to the top. Distance traveled by the block. Now let's see. I know that work is proportional to kinetic energy. So by extension, if I have something that's proportional to work, then that would also have to be proportional to kinetic energy. So let's look at that. Is our distance or time, do we know that either of those are proportional to the work done? Yeah. Work is force times distance. That's proportional. So as we go farther, say we go twice as far, we go some distance, then we go twice as far as that, the distance would be doubled. The magnitude of the work would be doubled also, because we have some amount of friction. That's not changing here, constant friction. And so the amount of kinetic energy that changes would be doubled as well. So on this one, it turns out the distance and the magnitude of the net work are the ones that fit. Time and speed, then, are the ones that don't fit. Time, we could figure out, doesn't work here. If we think about how the speed changes over time, we've got a constant force, so that means a constant acceleration. So the speed is decreasing at a constant rate with respect to time. So if this were a graph of v versus t, it would be a straight line like that. But remember, kinetic energy is 1/2 mv squared. So because of that squared in there, that would make it more like a parabola. It'd be a parabola coming, a curve kind of coming down like this. So A doesn't work here. So it's got to be B and D on this one. If you check the work that I do for this one online, you'll see that I have actually some equations worked out to show, oh yeah, the distance and kinetic energy, those are proportional, and here's the equation that relates the two. So you might find that instructive as you're studying this. Questions on 22? All right, we won't have a chance to finish this one, but we will take a little time to start this anyway, and you can read the rest of it at your convenience in the files that I shared. This is a question type that they used to throw in sometimes, the experimental design ones, but they've told us that every test every year from now on is going to have an experimental design question, or that's at least going to be part of the question. So designing a procedure in order to find some quantity, that's something that you absolutely will be doing on the test. Everyone had a chance to read through it? Okay. So let me just kind of talk through what they're looking for in the grading guide. I actually just copied and pasted the grading guide with an example on the document that's in that file. So that's a useful thing to check through. In this one, basically you're going to need to find the speed of cart A before they collide, and then the speed of the two after they stick together. Cart B is initially at rest, so we don't need to do any work to figure it out its speed. And then in our analysis here, we don't have to talk about the analysis on this one, but in the analysis, it'd just be mass of A times initial velocity of A plus mass of B times 0 equals mass of A plus mass B together times their final velocity. And so in that equation, once you measure the velocities, the only thing you won't know is the mass of cart B, and so you can solve for it. So your procedure needs to describe how you're going to figure out the velocity of A before the collision and the velocity of the two of them after the collision. They don't put restrictions on what equipment you can use, so whatever you want is fine. I would probably just put a motion detector in here. Set up a motion detector next to A and another one next to where they're going to collide, and figure out, make a measurement of velocity for A before the collision and a measurement of velocity for the two after the collision. Sometimes they'll give you a list of things that are available to you. Motion detector probably isn't going to be one of them, so maybe they'll give you like meter sticks and stopwatches, something like that. So then you can lay out, your meter sticks and say, okay, you watch this cart and time how long it takes to go a meter, and then, all right, you watch these two and you time how long it takes them to go a meter after they collide. And you can do distance over time to get the speed there. So what they're looking for there is that you identify what things you would need to measure to draw these conclusions, and then you have a method that would actually allow you to make those measurements. Yep.
Okay, so in the procedure you need to say so that you can, take these measurements so that you can, I don't know, you don't have to include the equations of how you would find them.
No, that's just what thinking I would do before I answered this one. They're going to be checking to make sure that you've identified the measurements that need to be made and talked about how you're going to make them.
Okay.
So if you forgot that, I'm going to need to measure the velocity after they collide, you lose points on that for not identifying that. So it's something you have to think about, but they don't specifically ask you to write about it here. So the grading guide on this one is something like, they identified that they need to measure the velocity of cart A before they collide. That's a point. They identified that they need to measure the velocity after they collide. That's worth a point, something like that. And then they talked about a reasonable procedure to do both. We're almost out of time, so I just want to talk through this one real briefly. The question is about uncertainty in your measurements and whether you're going to have that uncertainty when you make these measurements, whether that's going to be a bigger deal in the measurements before the collision or after the collision. So read through the statement. The top part is exactly the same. So just read through part B quick and we'll talk about it. So this one is really going to depend on what your procedure was in the last step. For the motion sensor one, I'd say you're probably going to be able to measure velocity before and velocity after with about the same level of accuracy. So on that one, the uncertainty between those two won't be significantly different, but you would probably want to say something like, after they collide, they're going to be moving slower. So that uncertainty in the velocity measurement, that's a bigger percentage of the overall speed at the end, after they collide, than it is at the beginning. So that's a bigger deal there. That's like when you time something with a stopwatch and you have that 0.2 seconds uncertainty. That's a really big deal if you're measuring something that lasts 0.3 seconds. It's not a big deal if you're measuring something that lasts an hour. I don't care if I'm off by 0.3 seconds over the course of an hour. But we think about percent uncertainty there. It's a bigger deal as our uncertainty becomes a bigger portion or a bigger percent of the measurement we're trying to make. If you were doing something more with the stopwatches and meter sticks, you could absolutely make an argument that the uncertainty on the front end of this, before they collide, is going to be a bigger uncertainty because, you know, that cart A is going to be moving faster. And it's tougher to see exactly when a fast object crosses this line and then crosses this line. On this one, they don't have a particular answer that they were looking for. Instead, I think it's just a one-point question, and the point is for picking one side or the other and for giving a reasonable justification. So it could take on a lot of forms. They just want to see that you've put some thought into uncertainty and how it affects your ability to draw conclusions. There will almost certainly be a question, not necessarily about like percent uncertainty, but about uncertainty in general on the AP test also. That was something that we should just sent out a document like 3 weeks ago saying, oh, by the way, this is pretty important. Yeah, great. I'm sure my fall students will really appreciate that. So everybody watching the video, this is pretty important. We talked about it in class. We did this with all of our lab stuff especially. But yeah, it would be nice to get that information a little earlier on. Way to go, AP. All right, guys, it's 5:04. Oh, my goodness. My wife's going to kick my butt if I leave too late here. So there are 2 more parts to this question. Like I said, I shared the files with you along with the grading guides in the solutions file. So be sure to check those out at some point. Our next meeting is about a month from now. I don't remember the date, but it's the 20-something of April. So stop in if you have questions between now and then, or send me an email, and I'd be happy to check in with you on that stuff. And keep on studying. Just got to do a little bit every day, keeping the habit of it. Thanks, everybody. We'll see you next time. Bye, Manu.